Everything we know about the universe tells us at that time there should have been equal amounts of matter and antimatter created. When the energy from the Big Bang cooled and coalesced into matter, there should have been equal amounts of matter and equal amounts of antimatter. But there isn't. We live in a matter universe. You're made of matter, you're made of matter, I'm made of matter. Where's all the antimatter? And that's what they're trying to find out at CERN and in various institutions, including China, all over the world. Where did all the antimatter go? As you know, when matter and antimatter collide, they annihilate. So why did antimatter win at the beginning of time? Why did matter win at the beginning of time? Very important not to make that mistake. Why are we made of matter? Why is the universe not made of antimatter? And the answer is we don't really know. But there must have been some tiny, subtle difference that meant that matter won out over antimatter. And that's what they're trying to find out. One of the things they've been doing at CERN, at the wonderfully named Antimatter Factory, is looking at how hydrogen and antihydrogen reflect light after you shine a laser on them. And they've found that, yes, they're exactly the same. But one thing they haven't found is how do they behave with gravity? So this could give us a clue. What were the differences to why there was that difference at the beginning of time?
So it sounds like the concept of gravity is pretty important here.
Well, it's one of the key things in the universe. So we have to be able to investigate it. It gives us something we can look at. We can look at light. You know, they know for 200 years exactly how hydrogen emits light when it's excited by energy. And so being able to, but with gravity, we don't know. We haven't been able to. And only now, after 30 years of trying, Jeffrey Hangst and his team at Alpha G experiment have been able to build antimatter, collect it in a magnetic containment, and then release it in such a way that we can see whether it falls to Earth in exactly the same way as matter. And within the precision of his experiment, which is nowhere near the precision of his light spectra experiments, he says it does. And that's a big deal because it starts to give us a clue, well, the difference at the beginning of time wasn't to do with gravity. It's something else we have to look for, right? So it doesn't tell us the answer, it tells us we haven't got the answer yet.
Well, let's talk about more questions and more answers then. What happens next after this?
He's got to get the precision. He's got to increase it. When he was telling me about the spectra 14 months ago when I visited the Antimatter Factory, when he was creating this G-bar experiment, this gravity experiment, he said we are down to 1 in 1,000 billion, 1 in 1,000 billion, 1 trillion precision in measuring the light spectra. But with gravity, they're nowhere near that. But the other thing that CERN and all physics laboratories want to do is they want to replicate. And there are 2 other experiments in the Antimatter Factory itself, which are going to use slightly different methodologies for measuring whether antihydrogen falls at the same rate as hydrogen. And once they all confirm this result, then the physics community will start to say, OK, we're really onto something here.
Neil, thank you. My brain's hurting now, so we're going to stop. Good to see you. Neil Cairns, the executive producer of CGTN, the science documentary show Razor.